This lecture is about how hearing takes place in the organ of Corti. So you remember the cochlea, and I'm just going to do a quick reminder of my unwound version here. So if I were to do a cross section through the cochlea here, what you would then see is a circle, and it would have a chamber there and a chamber here and a chamber here, roughly speaking. And this then is the scala vestibuli. You saw that before, that's there. This is the scala tympani. You've seen that before. So then here is the cochlear duct, and this is the one that we're going to be really concentrating on now, because it is in here that we see a rather interesting little organ. I'm going to draw too much of it here because I'm going to draw it in more detail in a moment. Here we are. Like so. So this little organ here by the way, again, that is the basilar membrane. And then there's an interesting membrane right inside here. This becomes important. That then is the tectorial membrane. And this whole thing, this whole little device here in the cochlear duct, this little organ then is the organ of Corti. So let's take a closer look at it then. So this then is a close-up then of the organ of Corti. Okay, so this is looking pretty good now. This is the tectorial membrane. These three things here are your outer hair cells. This is an inner hair cell. This is your friend, the basilar membrane. And this, now, these fibers coming out here, that is the cochlear division of the vestibulo-cochlear nerve. And then in here, just so you know, there are also some support cells, but I'm not going to bother drawing them in right now. So here you have the basic plan of the organ of Corti. So how does this turn into hearing? It goes like this. As pressure descends, actually, I'm going to put this, as pressure waves, I'm going to redo this. This will make more sense. As a pressure wave descends, through the basilar membrane, although it sets the entire membrane into vibrations, the maximal displacement, that is to say, the strongest vibrations, then the maximal displacement of the membrane, of the basilar membrane, then occurs where the fibers of the basilar membrane are what we will call tuned to a particular sound frequency. So the organ of Corti then rests on top of the basilar membrane, as I have shown you here. And the organ of Corti has cochlear hair cells supported by support cells. The support cells are basically all in here, just so you know. So those then will be your support cells. So we have the organ of Corti, and we have these cochlear hair cells there lying on top of the basilar membrane. And the hairs, which are known as stereocilia, project inward. Away from the basilar membrane. As you see here, here's the basilar membrane, and they're projecting in that direction. So the hairs are embedded, as you can see there, in the gel-like tectorial membrane, which you see here. I will even add that hangs overhead. And there are two different kinds of hair cells, as I indicated here. So there are 3 rows of outer hair cells, and there is one row of inner hair cells. And these cells have fibers leading to the cochlear nerve. Okay, so here's the business end of hearing. Here we have the cochlear nerve, the cochlear division of the vestibulocochlear nerve. This is taking information to the brain from the organ of Corti. So as I said, this somehow or another is now what we would call hearing, or at least it's on its way to becoming hearing. Whereas here we have a bunch of vibrations on a membrane. And the question is then, how do you get from vibrations in fluid to a nerve signal? So it goes like this. When the basilar membrane vibrates, the hairs bend. Here's where it gets crucial. First, in one direction, and then in the other. Let's take a look at what I meant by that. So here you have the tectorial membrane. Here you have a hair cell. Those hairs are bent in one direction. Here's our little friend, the cell. Here's the basilar membrane here. This is the hair cell. These are the actual hairs, the stereocilia. They're there and they're bending in one direction, as you can see. Then at some point we're going to have the same situation but it's straight. It'll be longer then, actually. Let me do that. That's kind of important. So then, as I said, when they're not bent, they're longer. Here we are. The whole thing gets bent. The whole thing is bending down. This. Here's the basilar membrane bending down. And then, when the basilar membrane, when that wave passes, and the hairs bend in the other direction. So as the basilar membrane vibrates, these little guys that are embedded in the tectorial membrane nonetheless wind up having those vibrations translated then such that they bend, the hairs bend first in one direction, then they straighten out, then they bend in the other direction. And so you have this bending in one direction, being straight, bending in the other direction, like that. So it's the movement of the stereocilia there. These guys here. Movement of the stereocilia in one direction. Sends nervous messages to the brain. So basically, when the hairs get bent in one direction, they basically say, I'm on. Then bending them in the opposite direction, shuts off the signals to the brain. So what this means then is that you will have different frequencies of these on-off signals. Remember, bent in one direction, basically this little cell here then tells the brain, I'm on. Bend the hairs in the other direction, and it says, I'm off. Or rather, it simply is off. So at a low frequency, it will go on, off, on, off, on, off. At a high frequency, that is to say, a high sound, it will then go on, off, on, off, on, off, on, off, on, off. So that then is how hair bending translates into frequency of signals, of nerve signals, that can then be sent to the brain by way of nerves. So the result then is that the frequency, literally the frequency, the how oftenness, the frequency of sound waves directly determines the frequency of signaling by cochlear nerve fibers. So that then, as I said, is how you wind up getting vibrations in the air being translated into vibrations in fluid in the inner air, which then gets translated into vibrations in these membranes, which then gets translated into hair bending. And it's the hair bending in one direction or another direction, on, off, on, off, on, off, which actually becomes a nerve signal telling about the frequency of those vibrations, that is to say, what pitch they are. And that then is what our brain interprets as hearing. And that's the end of this lecture.